Okay, so hello, my name is Vytenis, and I'm going to talk about organic solar cells, or to be more precise, about ultra-fast phenomena in such solar cells. Since I know that some of you know what organic solar cells are, but most of you probably have only heard about them and maybe have forgotten a bit, I will make a brief introduction so that the rest of the presentation would be a bit more interesting. So the basics of organic solar cells are as follows. You have two materials, usually it's polymer, some kind of polymer, which is electron donor, and we have a carbon football molecule, which is called PCBM, and it's an electron acceptor. We mix them both in a blend. We add contacts, and hopefully we get a solar cell. So next, when we shine light to this device, since polymer has much better absorption of light, it absorbs the light. That generates an exciton, which is basically an electron and hole pair, which are still attracted to one another. They cannot move freely. So in order to get some current, we need to transfer the electron to the PCBM phase, which can be done at a junction. So if we transfer the electron to the PCBM, then they can move. The charges are now free and they can move around, and so we have some current, or at least that's how it should work. Also, a very brief introduction to the technique that we used for our measurements. So the technique is called TRIFISH, and it is time-resolved, electric field-induced, second harmonic generation should be that on the bottom. So basically what it is that in an anisotropic material, like in a blend of two organic materials, you cannot generate second harmonic. But if you apply some electric field or some voltage to this device, that breaks the symmetry, and so second harmonic generation becomes possible. Now what is more is that, as you can see, our sample is quite like a capacitor. It has two big flat contacts. One is aluminum, the other is ITO. So it has two flat contacts and some material which isn't a very good conductor in the middle. So basically you have a capacitor. So once you apply some electric field, you charge the capacitor. And now if you use your pump pulse to generate some charges, and they migrate to their contacts, that discharges the capacitor. And so that basically what you get is a decrease in electric field in the material. And so you get a decrease in second harmonic generation. So basically what we can see is we can probe the electric field, the strength of electric field in such material with optical time resolution, which is in our case about 200 femtoseconds. Now we use this technique to try to answer a few questions. Especially, why do we need so much PCBM? Because basically we need about 80% of PCBM for good efficient solar cells. Although percolation, which is that every PCBM molecule is attached to the whole network of PCBM molecules, so that that percolation threshold is only 20%. So at 20%, basically, if you transfer an electron to PCBM phase, it should eventually find its contact, and 20% could be enough. But for some reason, we need 80% of it. Also, what influences charge generation and migration in such devices, and especially how do different polymers influence that? So to try to answer the first question, we used this TRIFISH technique to measure samples with different PCBM concentrations, from low to high, and before that we did our measurements on pure materials, pure polymer and pure PCBM, and that's what we get. So basically what you can see here is that in polymer, during first 3 nanoseconds we have extraction of holes because the holes have higher mobility in polymer. And later on, we have some extractions of electrons. Now in PCBM, we have very fast extraction of electrons, which is much faster, but it's only 20%. So that means that the rest of the polymers are trapped, the rest of the electrons are trapped somewhere. And later, at longer timescales, we have extraction of these trapped electrons and of holes. And also, what is also quite interesting is that if we zoom in this region, we can see that a polymer has a very intense, not very intense, but very fast drop in second harmonic generation. This is called excitonic drop, and it is because of the excitons which are generated in polymers. So basically, when you generate an exciton, it's a small, tight exciton. And under an applied electric field, it would try to stretch itself. And if it does, then the induced dipole moment would be in the opposite direction, and it would decrease the electric field in the device. And so that's where we get that excitonic drop. Because in the polymer, which is conjugate system, the exciton can stretch quite wide through the polymer chain. In the PCBM, meanwhile, we did not see that excitonic drop because it's a small molecule, so the exciton has no room to expand, basically. And what we will also see is that even at the lowest PCBM concentrations that we used, there is no excitonic drop. That means that electron transfer to PCBM is very efficient and very fast. It's comparable to our time resolution of 200 femtoseconds. So here you can see that there is no excitonic drop in either of these samples. What you can also see here is that as we increase PCBM concentration, the initial mobility increases. And so when PCBM is just like 33%, here we have mostly the motion of holes, and later on the motion of electrons, just like in pure polymer. Just the problem is that in pure polymer, that value reached 40% here. And here it's only 20% or 30%. That's because PCBM makes it harder for holes to move through the polymer. Now when we have 50 to 50 PCBM and polymer, now the initial mobility is much better because it's a combination of electrons and holes that are moving. And we see that the charges are extracted, almost 60% of the charges are extracted, and the rest of them are extracted also quite efficiently. Now when we have 80% PCBM concentration, we see very fast extraction of carriers, which are basically electrons, because this high mobility is attributed to electrons. So what we can see is that at about 1 nanosecond, we have 50% of the charges, and most of that are electrons. So basically all electrons are extracted from the solar cell. And later on, we see the extraction of holes, which is still slower than that of one-to-one sample, because the holes which are moving in the polymer have now some difficulty to find a good pathway. Now we can say that these are mostly electrons here, not only because it has a high mobility, but also because we did measure the pump probe kinetics, the transient absorption kinetics of this sample. And here at 900 nanometer detection wavelength, which is attributed to holes, we can see that it doesn't even start to decay until at least 10 nanoseconds. And it doesn't decay at least until a few hundred nanoseconds. So basically here we see that these must be electrons which are extracted here, because holes take much longer time to be extracted. And we also did a summary of quantum efficiency, internal quantum efficiency of our devices. And what you can see here is that on their own, neither PCBM nor the polymer which we used, they are not very good at all at being solar cells. So we have to mix them up together. And our best sample is that with 80% PCBM concentrations. And at 2 volts of applied voltage, it already saturates close to 90%, maybe 80%. That shows that neither charge generation nor migration can be increased, made better by applied voltage. Meanwhile, the next sample, which is 50 to 50, reaches this value only at about 3.5 volts. So twice as much voltage is needed to extract the charges efficiently. Also, we tried the same experiments with different polymers. So these are the polymers which were investigated. And our initial results are like this. It appears that it doesn't matter for the electrons which are moving through the PCBM phase, the fast initial phase of extraction, doesn't matter what polymer we use. So basically, the conclusions of our results are that electron mobility increases with PCBM concentration, even though percolation pathways exist in the lowest concentration samples. And that's mostly because PCBM at high concentrations, it generates clusters which make it much more easy for electrons to move. And also, polymer does not influence the mobility of electrons in the PCBM. So it may influence the mobility of holes, but not mobility of electrons. And with that, I would like to finish and thank my collaborators. So this is our group in Vilnius, in Center for Physical Sciences and Technology. And I would especially like to thank Ingjot from Lund University and Armantas from Linköping University, who made the samples for our measurements. So thanks.
Can you return your presentation on 4 slides with this one?
Yeah.
What does mean the negative quantum efficiency?
Yeah. Okay, I thought you would ask that. Basically that means that when the applied voltage is on the when we applied negative voltage, just the current flows in either direction, and that's all. Basically, the values are correct. The minus sign is just, it doesn't matter. Because as you can see that the zero efficiency is not at zero applied voltage, it's at -1 because of the internal electric field of the devices. So.
Other questions? No? Thank you very much.